gold. One of the most, if not the most coveted commodities in existence today. We use it in our jewelry, electronics, satellites, and in medicine, to name a few. Probably the most recognized geological gold deposit is found here in South Africa. A country, immensely rich in resources and minerals, South Africa's total reserves remain some of the world's most valuable. Overall, it is estimated to have the world's fifth largest mining sector in terms of GDP. With South Africa's economy built on gold, platinum, and diamond mining, the mining sector is an important foreign exchange earner, with gold accounting for more than 1/3 of exports. Located in the northeastern district of South Africa lies the Witwatersrand Basin, its stratigraphy revealing the occurrence of distinct layers, providing clear evidence of its history. The basin measures approximately 300 by 150 kilometers in an elliptical shape, and is considered to be the richest deposit of gold ever discovered. It has so far been responsible for the production of more than 2 billion ounces of gold. Here on the northern border of the basin, between Johannesburg and a mining town called Carletonville, we find the Goldfields South Deep Mine. Superimposed on the surface, we can see the outline of the Upper Ellsberg Reef package in blue. The ore body is divided into Old Mine, Current Mine, and North and South of Wrench, which are divided by the Wrench Fault. North of Wrench constitutes the strategic plan for the near future of mining at South Deep and will be the focus of this visual experience. South Deep is the world's second largest gold mineral resource, and the life of mine extends to 2087 from an economical viability point of view. 70% of the group's mineral resources are found here at South Deep. The mine has two main access points to the ore body below. South Shaft was initially developed to provide access to the Old and Current Mine. Since the development of the Twin Shafts complex, the South Shaft serves more of a support function. Most of the current operations occur at the Twin Shafts complex, of which the main headgear and vent shaft can be seen in front of you. The mine's surface infrastructure consists of several workshops and refrigeration units for ventilation. In addition, the gold processing plant is situated not far from the headgear. The gold plant uses a conventional process flow which consists of milling, carbon in pulp, elution, electrowinning, and smelting. The resulting gold ingots are then transported via helicopter to Rand Refinery for refining. The Witwatersrand Basin consists of several layers of sedimentary rocks referred to as groups, with the Pretoria Group closest to the surface. To give an estimation of depth of the South Deep mining operations, you can see 3 football fields to scale, which are equivalent to 300 meters. The ore body is within the Central Rand Group at a depth of roughly 3,000 meters. If you look up, you will see we have raised the surface of the mine to the equivalent of the depth of the mining operation. To access the reef, the main shaft has been sunk down to 2,990 meters. Let's now take you underground to have a closer look at the ore body. Shown here is the Upper Ellsberg Reef package, located at the base of the Ventersdorp Lavas Group. The reef package forms a wedge shape reaching a height of 120 meters at its maximum. The left side of the reef package subcrops onto the Ventersdorp Contact Reef, commonly referred to as the VCR. The VCR is where the majority of gold mining in the region has historically occurred. This is done at widths of between 0.5 and 3 meters. The Ellsberg Reef lies at an inclination of 14 degrees and is situated almost 3 kilometers underground. To the north, lies the Current Mine, which has been responsible for the majority of the production. The north of Wrench, however, will contribute the bulk of the production over the next 30 years. The The reef stretches almost 3 kilometers along dip and almost 1.5 kilometers along strike. To the right you can see the south of Wrench mining area, which forms the long-term strategy for the operation. This provides an additional 50 years life of mine. South of Wrench is separated from the north of Wrench by the Wrench Fault. It therefore lies at a different angle, with its lowest point reaching a depth of 3,300 meters below the surface. Significant efforts have been made over the last decade to de-risk the ore body. As a result, the South Deep ore body is one of the best understood ore bodies in South Africa. All these geological properties were considered in determining the mining strategy. Let's show you how. The Upper Ellsberg Reef package consists of 16 different reef units or horizons, all containing different grades. By looking at values of grades, and the costs of mining methods, specific areas of the reef horizons are chosen. These specific areas are of interest to the mine and are called reef targets. This is where the majority of the production activities are focused. It is close to the subcrop where the largest concentrations of gold per volume can be found. The size of the ore body and the concentrations of gold in the reef targets are why the ore body is exceptionally suited for massive mechanized mining. Because of the massive depths of the ore body, and the prevailing stresses in the host rock, the ore body is divided into corridors by regional pillars left in situ to support the strata above. Each pillar spans 60 meters across, and divide the ore body into 180 meter wide corridors. The South Shaft complex connects to levels 90 and 95 and services the old and current mining operations. No rock is hoisted to surface here. Its primary role is to provide ventilation and support the mine's backfilling operations. Levels 90 and 95 were developed from the South Shaft to the twin shafts. They are responsible for the track-bound ore handling from old and current mine. 93 level is predominantly an infrastructure and support services level containing the main equipment workshop. This workshop can be seen highlighted in blue. The main workshop is roughly 200 by 250 meters. It contains several important areas such as offices, the repair and service bays, and oil and diesel storage. Vehicles moving out from the main workshop are shown by icons. The icons coming down the twin shaft are the miners at the start of a shift. The 100 level currently services track-bound ore handling for current mine. In the future, the rail-bound system will be replaced by trackless equipment feeding crushing and conveying systems. Once the ore is tipped, it is crushed on 100 level and makes its way to the surface via a series of conveyors and silos. Several cuts are made into each corridor and are where de-stress mining takes place. To access these cuts, a spiral ramp system is built under each corridor, connecting the cuts to the various development levels. These spiral corridor developments contain several satellite workshops and shift weight areas. The parts of the development shown in blue and red represent airflow in and airflow out respectively. They also contain ore passes where mined ore is tipped and transported by truck to one of the crushers. The vent shafts are there to provide ventilation to the main de-stress mining operation. De-stress is the concept of lowering the stress levels surrounding an excavation, by redirecting those forces away from the excavation. Shown is a simplified schematic of how geotechnical stresses surround an excavation. In red, we are shown stresses represented as lines directed vertically downwards, as the major stress component is vertical in this case. Pay particular attention to the density of the red stress lines at the edges of the excavation, as higher density represents higher danger for stress-induced failure. Notice also the sparseness of stress lines in certain areas, shown in green. These areas are deemed to have been de-stressed. An excavation in this area is safe to be mined, and stress levels present resemble that of an excavation of roughly half its depth only. As the excavation advances, it is clear how the stresses surround the excavation, and why the particular shape of advance is formed to minimize catastrophic stress-induced failure. The wider the excavations, the more stresses are deferred. These deferred stresses are directed through regional stability pillars of exceptional size, in order to stabilize the area of workings. Now, let's see how this de-stress mining occurs. In order to better understand the mining principles and methodology of South Deep, we will look closer at a portion of the ore body. In this case, a single corridor. Here a cutaway portion of the corridor is shown, flanked by regional stress pillars. The following sequence shows the de-stress development for a single cut in the corridor. The layout here is a variation of the herringbone de-stress design. This layout advances in an arrowhead formation. The development area is geotechnically safe, shown by the red stress lines parting. These stress lines are redirected through the regional pillars by the advancing de-stress development. The main access drive leads the advance and creates access into the cut from the ramp. Stope access drives break away at acute angles to the main access drive. These drives extend up to the regional pillar. Being a mechanized mine, South Deep utilizes a suite of trackless machinery to do its mining. The number of vehicles allowed within a cut at any one time is restricted by ventilation limitations. Let's take a closer look at the equipment used to do de-stress development. The mining cycle starts with a recently cleaned and supported end. A double boom drill rig drills the face to ready it for the charging phase. Drilling is done horizontally when de-stressing. Charging occurs with a utility vehicle, equipped with an explosives charging station. After filling with emulsion, the holes are tamped and charges are set. The mine is cleared and all awaiting blasts are set off sequentially. The blast pulverizes the rock to an almost gravel-like consistency. After a specified re-entry time has lapsed, the ore is then loaded by a manually operated LHD, after which the ore is tipped in the nearest ore tip. This takes several loads until the end is cleaned. Once the end is cleaned, scaled and barred down, another drill rig meshes and supports the structure of the excavation. Technical services can now measure and plan corrections if required before the cycle is repeated. By repeating this cycle, the de-stress ends advance until the drive is completed. All drives are mined using the cycle just shown, according to a schedule developed by the South Deep Planning team. Here we can see multiple cuts developing simultaneously. The cut above de-stresses the cut below, and vice versa. During steady-state operations, 3 of these cuts are mined in parallel. A typical corridor will consist of between 10 and 20 cuts over its lifetime. Footwall development can now proceed within the de-stressed zone. This system is repeated for each cut within the corridor. Once sufficient de-stressing has occurred within a cut, it is geotechnically safe to commence with long-hole stoping. This is done using a long-hole drill rig. Let's take a closer look. The long-hole drill rig is shown here drilling holes for injecting emulsion. The first array of drill holes are spaced tightly together. This section of the stope is called a slot raise. The purpose of the slot raise is to create a space for the subsequent blasted rock to break into. The slot raise is only drilled at the end of the stope access drive and is not repeated within each stope. Stopes can reach a height of between 15 and 35 meters. The utility vehicle charges the drilled holes with emulsion. Charges are tamped and set, and the mine is evacuated for the impending blast. The slot raise is blasted and an LHD is used to clear the muck pile. Unlike the horizontal de-stress development cycle shown earlier, there is no supporting in-between blasts for long-hole stoping. For this reason, personnel are not allowed into the blasted area and thus loading is done remotely. The cycle repeats for the mass blasts with rings being drilled and blasted. The spacing of the holes when drilling the rings is crucial to obtain optimal fragmentation when blasting. Days, unlike de-stress blasting which occurs at every shift. This is due to the amount of cleaning and preparation involved. The LHD is controlled remotely through line of sight with the operator a safe distance away. Exposed drive entrances now have to be barricaded before backfilling may begin. The main purpose of backfill is to provide structural stability to the excavation. Backfill mix constitutes tailings from the plant, mining waste, cementation product, and aggregate. The backfill and curing process takes around 70 days. Once cured, the adjacent stopes will be mined. Here you can see a sped-up long-hole stoping schedule being developed. In this sequence, green blocks represent stoping while gray represents stopes being backfilled. Note that de-stress has already occurred from the center towards the pillars. Conversely, the long-hole stoping process retreats from the pillars towards the center. The portion of rock above the main access drive is left undisturbed for regional stability. Up until now we have seen how mechanized mining plays a central role at South Deep. The next phase of the process involves transporting the ore to the surface. We will now follow the ore on this journey. We begin our journey back to surface from within a cut in a typical corridor. Ore from both de-stressing and long-hole stoping is trammed using an LHD to an in-cut tip situated at the top of an ore pass. Here large rock fragments are broken by rock breakers to fall through the grizzly. At the bottom of this ore pass, dump trucks are loaded at a box front. The trucks then haul the broken ore up the access ramp to the crusher system. The dump truck travels to an available tipping point at the top of the crusher installation. Each installation has 2 tipping points to reduce truck congestion and queuing delays at the crusher. By crushing underground, the transportation, handling and storage of the ore can be done in a safer and more efficient manner. The crushed ore is stored in the silo below the crusher. From here the conveyors continue the process of transporting the ore to the shaft complex. During the crushing process, large magnets are used to remove any unwanted metal from the ore, such as roof bolts used in supporting. This is done to reduce wear and tear on the conveyor belts. Crushing the ore into smaller fragments increases conveyor mass throughput due to increased packing density. In much the same way a glass can hold more crushed ice than ice cubes. From the conveying system on 105 level, the ore passes through a set of silos to another conveyor system on 110 level. The last leg of conveyor belts on 110 level deliver the ore to the loading station. From here the ore is hoisted using skips to the surface using twin main and twin vent shafts. For the final portion of our journey, we are joining the rocks in a skip for the 3-kilometer trip to the surface. Looking back you can see the trail of how far the ore has traveled during this journey. This trip consisted of almost 1.5 kilometers by dump truck, 1.5 kilometers by conveyor, and 3 kilometers by hoist. The distance traveled took approximately a week. An ore body like South Deep's holds immense value. But that value can only be realized if the gold is mined and brought to the surface. Today we have given you insight into how the Goldfields South Deep team does that. But while gold mining is our core business, our purpose extends far beyond simply getting the gold out of the ground. We are here to unlock the value of gold and channel it to our investors, our employees, our communities, and the economies where we operate. This lies at the heart of Goldfields, to share value and, in so doing, to ensure sustainability. Thank you for joining us on our virtual reality tour of South Deep. We hope you have enjoyed the experience.